Hi everyone. Hi everyone, my name is Rafał Foltyński and welcome to Lightning Talks. Today I'm going to talk about buffer recycling. If you want to join and join the slido.com to ask some questions, I'll try to answer them in the end. It's a lightning talk. I have tons of slides, so I may talk a bit fast. I hope you manage to keep up and enjoy the ride. So before we start, I'm a senior consultant in Amido in London. Also, I'm an open source contributor. I will talk a bit about it today. So I'm going to tell you why am I here. I'm going to present you a non-pooled example. Also tell you something about object pooling theory. Present some pooled example, and then give you some extras, some GC comparisons if you manage to get some time for that. All of this stuff in the context of my open source plugin called Log4j to Elasticsearch, which is a Log4j appender that is capable of pushing logs in batches to Elasticsearch cluster directly from your application. So I've noticed that when this library runs, it allocates a lot of memory, and I decided to tackle that using a pattern called object pooling. So when you think about a real-life example, imagine that you have a birthday party with lots of guests, really lots of guests. And every guest grabs a drink in a plastic cup. After he finishes his drink, he just puts the cup on the table and grabs another cup. So you will end up with a lot of cups. A lot of garbage. Now, in analogy to batch log delivery, when you log any information from your application, the log4j event will eventually get serialized to a JSON, allocating some strings, and then it will get added to a big bulk requests, where each of the lines represents the type of operation that you want to execute in Elasticsearch and the actual payloads to execute. So, question to you. You probably know these two lines above, right? Anyone? Yeah. So there's a problem with these lines. We use it a lot in production, but they allocate a lot. They allocate a string, and they allocate a lot of garbage underneath. If you are familiar with the line above, that's great. If you're not, keep it in mind because it will be useful in the next slides. So the architecture of this plugin. Once the log reaches the appender, it gets serialized by a serializer. That's where the first allocation happens. Then the serialized log gets the batch delivery. It gets stashed in the memory store. Once the amount of items in the memory store reaches some threshold or some delivery interval has passed, it will be sent asynchronously to the listener, where another serialization happens and another huge allocation happen while generating this huge payload that will eventually get passed to the HTTP client and delivered to the ES cluster. Let's have a look at the demo if we can. I'm going to start with a non-buffered version. So there are potential issues with high memory allocation. It can lead to a situation where the garbage collection has to deallocate this memory in a quite short intervals, causing stop-the-world pauses, and eventually leading to out of memory errors when the amount of garbage collection is actually so high that your application cannot keep up and starts to behave in a unpredictable manner. If you ever see this in your stack traces, in your logs, don't mask it with the flag mentioned above. Just fix your stuff. So let's have a short chat about object pooling now. because these issues can be addressed using this pattern. The basic most popular usage of object pools is to store long-lived objects that are quite heavy or take a lot of time to create, but it can also be applied for short-lived objects when the amount of these objects is so huge that it starts to impede your application performance. There are numerous recycling patterns. I'll explain borrowing and reference counting. In case of borrowing, you physically remove the object from the pool, and the borrower is responsible for putting this object back in the pool. There's also reference counting, where the object is not physically removed from the pool, but internally the pool will never lend it to another borrower until the count actually reaches 0. There are multiple allocation triggers. The easiest one is on empty, when your pool is actually exhausted. The problem with that, the risk with this approach is that when your object actually takes a lot to create, the actual borrower that hits this moment will wait a lot for another object. That's why you can do that preemptively. You can use the load factor. If your pool is exhausted in like 80-90%, you can pre-allocate it. You can pre-allocate some objects somewhere in the background, or you can use more advanced algorithms analyzing lease and return rates to actually predict when your pool will run out of objects and allocate preemptively. Let's try to have a look how our non-pool delivery went. So you can see that the actual blue areas represent the amount of memory, and each 30 seconds there is a young generation that cleans up this memory. And let's try to run the pooled example to actually address it. So once you decide to resize your pool, there are multiple resize strategies. You can use a fraction of the initial size. For example, if your pool has had 100 elements and you decide to resize it by 50, you'll get 150, 200, 250, and so on elements. You can decide to use fraction of the current size, which would result in a pool being expanded to 150, 225, and so on. Or you can decide to not resize at all and force the borrower to actually handle the situation on its own. The real life example, when you have a party, you can put a tray of glasses. Every time a guest finishes a drink, he puts the glass back to the tray, allowing other guests to have a drink, if they're okay with hygiene, obviously. So in the architecture of this plugin, I decided to add a couple of pools of byte arrays, pools of buffers, right next to the places where the serialization or some huge allocation occurred. Borrow the buffer, serialize the JSON into the buffer, pass it over to the HTTP client. Once the request is done, just release them, put them back in the pool. I got super excited about this idea. Imagine allocating like a huge byte array, start to slice it, start to manage it, borrow it to different borrowers, compact it. You'll basically write your own memory management system. I decided to share this idea with community. Fortunately, a bunch of guys on the meetup that I've met were working for LMAX Exchange. These are the type of guys, when you talk to them for like 30 seconds, usually your brain starts to fry. I shared this idea with them. Their eyes started to grow, and they said, "Dude, no, don't do that. Just use Netty, all right?" It was already done. But all right. But I wanted to run my pool. But okay, let's have a look at Netty. Yeah? I found an interesting buffer inside Netty buffer jar. Do you know what's the result of this code? What do you think is the result of this code? Anyone? All right, so we initialize the buffer with the size of 2 bytes, and then we write hello GeeCON into it, which is of size of 14 bytes. But the composite byte buffer will dynamically resize, never throwing any errors. I thought that's the perfect buffer that I'd like to have. Why would I ever want to write my own? Good stuff. So I compared the approaches. Should I write it from scratch? I had a look at Netty. I had to look at the actual complexity of the code in the Netty, all these weird quirks, all these different operations that were happening during writes of different object types, and I thought writing this stuff from scratch would take really long. Management of expectations would be difficult because I promised this object pool to be implemented until the end of last year. Fortunately, I managed to do that. Had I started to write it from scratch, I would probably release it around Java 27. So you can create your own buffer, your own composite byte buffer. You can wrap it in a byte buff output stream and use the Jackson writer to write your value directly into a buffer. You can also borrow this object, borrow your own object of your own API, which wraps the byte buffer, and do the same thing. So my expectations towards the pool that I wrote was that the API has to be reusable. I would like to use this pool for different objects. I would like to pull anything I want. I would like it to be simple to use. I would like this pool to expand and shrink automatically. I've chosen an empty strategy because it was the easiest one. And once I hit this moment and I create 5,000 more buffers, it takes like 2 or 3 milliseconds. So it's like, all right. And let's see how it went. Sorry, it's the epsilon example. Anyway, I allocated 1 gigabyte during delivery of 1 million logs, which is a significantly lower amount of memory that was needed to deliver this test. So it meant that the intervals between STW pulses will get increased. The memory allocation will get reduced, but I would have to be very careful about not generating memory leaks and not leaving the glasses out of the tray. I decided to scale up a bit and deliver more logs. Have a look, what's the actual overhead of this approach? So logging 5,000 messages of 1 byte via this framework takes roughly half an hour to complete. On the graph above, you can see the non-pulled version. On the graph on the bottom, you can see the pulled one. The green line represents the amount of time spent for the GC to actually do the either the allocation or promotion operation. The spikes that you see on the left are the spikes right after the start of the application. So for the purpose of this presentation, I'm going to use the middle one, the middle part of the graph where the actual GC got fairly stable, and we can easily see how this approach performs in the regular conditions. So in 30 minutes from 260 milliseconds that I spent doing GCs over 49 collections, it dropped to 220 milliseconds, which was a good win. Problem was that the average pause increased slightly, but the overall amount of freed memory per minute dropped almost 4 times. That was a nice win. I decided to log a bit bigger messages of 200 bytes, and numbers got much better. The average pause right now is 7 milliseconds for the non-pulled version and 9 milliseconds for the pulled one. But the amount of freed memory dropped from 80 gigabytes to 11 gigabytes. Accumulated pause, 1 second versus 210 milliseconds. I decided to scale up even more. Log 1 kilobyte messages, and now we can see that the string approach, where we allocate a lot of stuff on our heap, eventually will cause a lot of promotion and major GC, which in this case took roughly 4 seconds to complete. When you try the same workloads with the pulled approach, you get a very decent flat graph. It means that your application throughput is potentially increased. Numbers got even better if you take 5.96 hundredths of seconds, deduct the major GC. You will get roughly 2 seconds versus 600 milliseconds with the pulled version, and the average pause of the pulled version with 1 kilobyte logs was roughly 5.5 milliseconds. You can notice that the average pause interval with the non-pulled version shrank to 3 seconds, which means that if I increased the load, increase the traffic, or increase the Hello?
Second.
Hello? All right. Which meant that if I increase the traffic or increase the log size, the application will eventually run into a situation where it will have huge problem with removing the garbage. And I decided to scale up even more. I pushed 100 million logs. It took roughly 5.5 hours to actually push it at a rate of 5,000 messages per second, but I couldn't even fit the whole graph here. But you can see that it's like quarter of the whole graph, and the numbers for me actually were staggering. In 5.5 hours, I spent 6 seconds, roughly 6 seconds to do over 1,000 collections with 5.5 milliseconds collection time. So you may think 5,000 messages of 1 kilobyte in size decreased from roughly 6 seconds per hour or 12 seconds per hour to 1. Looks like a huge win, but was it actually worth the effort? That is a decent improvement. It's a very nice improvement, but if you work in a company that is oriented towards feature development over solution engineering, this sort of engineering can be tagged immediately as premature optimization, or some people can say that the perfect design is the enemy of good. But the library was delivered. It works on multiple servers right now on client sites, and right now 80% of stuff was delivered. Time to tackle the 20. The 80-20 rule applies. And ultimately I had a lot of fun and I learned a lot. And this improvement is only the beginning, because I'm planning to get it even lower with that. Thanks a lot for your time. I hope you enjoyed it. And do you have any questions? Is it possible to handle 100K allocations per second without concurrent modification exception? Yes. The concurrent modification exception error got fixed. It was an issue with a third-party library called Jest. I just rewritten it to be properly concurrent. And but 100,000 allocations, that's a huge traffic. That's a huge traffic, and if you have a machine that is big enough to handle that, you can try. I managed to handle 5, 10, 20,000 per second, and over that, my poor laptop is just not good enough. Elasticsearch just cannot cope with the ingestion. Is it possible to make Hibernate ORM use object buffer? I don't know, probably. If you spend enough time digging through the code, digging through the open source code, you may find ways to do really weird stuff and replace really critical components with your own ones, and eventually you may end up contributing back. Can you make slides available on Twitter? Of course I can. Will do. Any other questions? All right. Thanks a lot for your time, and see you next time.